not sure if he ever figured it out.
Hopefully nobody ever told him.
Right, eventually. There's one kid that told him that. Just a kid.
Bad news. Ulrich, we're gonna need you, man.
That's fine. It's already recording.
Yeah.
Don't send this to my biochem or my microbiology.
Probably still
He probably still is doing the exact same.
What if he
Why in the world is everybody doing so?
Yeah.
They're all sleeping. I remember I remember a lot of things. I like but I do remember sitting in class making little tick notes.
Yeah,
marking every time he said because he said all the time.
They do the smallest ones that we have right now.
So every day. Now I'm gonna catch myself doing it 45 times in class.
I'll make
Thanks. Let me know. Let me know how I do. Let's go ahead and get started.
Oh, we got you to work like that.
What are you talking about?
We had to use
I don't think so. We're done. Chapters 3 and 17 I kind of lumped together. We'll get about halfway through chapter 3 today. We'll finish chapter 3 on Friday and chapter 7. We'll get about today's Friday. Welcome. Good morning. We'll finish chapter 3 on Monday. We'll probably finish chapter 17 on Monday. There are only a few things, a few terms that we're going to define. After we finish chapter 3, you're going to think you're sitting in a biology class. Not really, because we're going to talk about a lot of the chemistry at each step of these pathways. But we are going to look at the same some of the same pathways we looked at in other classes. This is what I didn't like about biology. Every single class, it seems like you did the same thing, like 90% of each class. That's cool. You like that? That's boring. Review. But most, you take another class, and a lot of it is review from your previous class. Another class, most of it is review. Anyway, so you're going to feel the same way again. So biology majors specifically tend to do better on this class exam because it's content you've seen before. You probably haven't gone into it in the depth that we're going to go into it. Each step in the depth that we're going to go into each step of these pathways. But they are pathways you've seen before. They're pathways you know where they're found. You know what they do. You know what they contain. So it's usually an easier transition. Most biology students much better on exam 3 than those who don't want into. But until then, bioenergetics. Chapter 3 and 17 in Biochem textbook. In the literature textbook, this is chapter 13, I believe. It's the bioenergetics chapter. There is no chapter 17 in the Biochem. In the literature textbook, there is no chapter 17. Before chapter 13, you'll see like 3 or 4 pages. It's a little kind of brief overview of metabolism. That's basically the same content that's covered in chapter 7. So right before chapter 13, there's a little section about metabolism. All right. Thermodynamics, bioenergetics, and ecological systems. Review of basic concepts of thermodynamics. You have talked about terms of thermodynamics in terms of Gibbs free energy. In terms of enthalpy. The amount of energy required for a reaction, or the amount of energy available, left over, or required from a chemical reaction, the heat content of said reaction, and the degree of randomness of the molecules participating in this reaction. Talk about it. You have Jin Kim talked about delta G gives the change in Gibbs free energy of a reaction in terms of favorable, unfavorable. A delta G of 0 would be a reaction at equilibrium. A positive delta G would represent an unfavorable. Whereas a negative delta G would represent a favorable reaction. But in terms of biological systems, we represent the change in free energy as a function of two things. And it's not going to make sense when I say it first. If you haven't read the chapter, you should have read the chapter. Right? You should start reading before class. The term standard state versus non-standard state may sound a little weird, but we'll define these terms in just a second. Delta G, the biochemical reaction, is a function of the standard state free energy change. RT log equilibrium. For equilibrium of a system, A plus B, 1, 2, C, D. This is also we did this in the first chapter. The product of the concentration of products, or the product of the concentration of reactants. So a few questions. What are these terms? R is our ideal gas constant, 8.315. T is our temperature in Kelvin. Somebody pointed out to me earlier that I did all of my calculations at 25C, room temp, which is, that's not physiological conditions, right? So I didn't change that for today. So when I do these calculations, I call like my temperature at room temp. Yeah, that's weird. Should have done that, right? Should have done the physiological condition. I'll make a note, and next time I'll do it physiological condition. And lastly, what do we mean by standard state? And what do we mean by the change? So delta G naught, the change in standard state free energy. So delta G is a function of the conditions of the reaction. Delta G naught is our what we call standard conditions. And what are these standard conditions? It is the free energy change. Standard conditions, we assume standard state, as in red, standard state is pH 7.0. Concentrations are 1 molar concentrations. 1 molar concentrations, pH 7. However, 1 molar concentration does not apply to hydrogen. What would the concentration of hydrogen be? And then -7, right? pH. So when we talk about concentration of reactants and concentration of products, if hydrogen is a product or if hydrogen is a reactant, we're not talking about hydrogen. We're also, if water is a reactant or product, we're not talking about hydrogen, we're not talking about water. We're not talking about the concentration of hydrogen, we're not talking about the concentration of water. The concentration of water is 5. 55, not 1 mole. Concentration of hydrogen, 10.7. This is a weird concept. I mean, hopefully what we're going to talk about today clarifies it and you're going to understand what we're talking about. We're talking about the change in standard state free energy versus the change in free energy of the system under physiological conditions. If afterwards this still doesn't, it's not good. Page number. On page 58, in the bottom left-hand corner of your biochem textbook, there's a nice little figure there that it does a pretty good job. It describes the difference of equilibrium systems versus standard state systems versus physiological systems. It kind of gives you it gives you one setup and describes it 3 different ways and shows you at these different concentrations what it's going to look like and what your free energy change will be. And it works. I don't think it's the clearest way, but if what I say today doesn't make any sense, look at that figure, and maybe that figure will make a little bit more sense. It explains what we're fixing to talk about in a completely different way. It's also true. So So if you're still confused after today, please go look at that. It should help. And I was telling everybody yesterday, at the beginning of class, like we were going to derive everything. We were going to do math. And at this point, we're a little behind. Plus, we got other things. So at this point, I'm going to give you and tell you, you know what? If you can derive these, you're in good shape. If you can't derive these, at least know these equations. At equilibrium, delta G is equal to 0, right? We said that all the way up here. Delta G is equal to 0. Equilibrium. In that case, I can rearrange this equation because if this is equal to 0, I can rearrange our equation to solve for delta G naught for equilibrium, right? So two useful derivations of this equation. At equilibrium, delta G naught is equal to minus RT my equilibrium. Equilibrium is equal to 10 minus G naught over 2.3 RT. And yes, you should be able to derive those things when we get to 1440. When we get to Biochem 2, loves for Biochem 2, these are things you'll be expected to be able to do. So what does all of this mean? All of this means in a standard state system, if our equilibrium is greater than 1, our delta G naught is favorable. In a standard state system, if our equilibrium is greater than 1, our delta naught, or our delta G naught is favorable. If it's less than 1, standard state free energy is not favorable. Surprisingly, most biochemical reactions have positive delta G naught values. This means they're unfavorable, right? This means they're unfavorable. So we're going to talk about two ways biological systems overcome this unfavorable, sometimes small, sometimes large, unfavorable delta G naught value. You know these reactions take place, right? So what are some ways that they overcome this? The examples we're going to be using are steps in the various pathways that we're going to be talking about in the next few weeks. So hopefully we'll be killing multiple birds with single stones here, because we'll come back to these systems a bit. Dihydroxyacetone phosphate is a product. Glycolysis. It's not a very useful product. Lies in an equilibrium with a useful product. You may see this drawn multiple ways. You may see this drawn OH or an O minus. Why? Because the pKa is close to physiological conditions. If you look at our textbook, it's probably drawn closer than protein. It's complex to make everything equal. Yes, thank you. This lies in equilibrium. And more useful. Glyceraldehyde 3-phosphate. And this is the same example your textbook gives on page 58. It talks about this system, and it talks about this system at equilibrium under steady state conditions, under standard state conditions, and under various physiological conditions that they made up. So how do we compare this system? If we look at the delta G naught of this system under standard state conditions, pH 7, concentrations of 1 molar, what does this look like? What is our delta G naught under standard state conditions? So standard state in green. Under standard state conditions, equilibrium, this system is 0.047. Standard state conditions. So from right there, what can you tell me?
It's less than 1.
It's less than 1, right? So is this a favorable delta G naught? Unfavorable. Unfavorable, right? Equilibrium is less than 1. It's not likely under normal circumstances to proceed to the right, right? I just pointed to my right, which is your right. So that's kind of weird. We calculate this. Delta G naught is equal to negative RT ln of my equilibrium, right? Negative RT ln of my equilibrium. Our plug-in numbers, negative 8.35 times, and then again here, bear with me. I did my calculation for some reason. 298 natural log of my equilibrium is 0.47. 7.5 a fairly positive delta G. Delta G is positive 7,550 joules per mole. However, under physiological conditions, my concentrations are not always sitting at this equilibrium. Why? Because we're not at pH 7. We're not at 1 molar concentrations. Anything, probably, most likely. Under physiological conditions, we assume pH AP is equal to 2 times 10 4th molar phosphoryl 3-phosphate is equal to 3 times 10 6 molar. We can calculate this value. We can calculate what is our delta G. If we want to calculate the delta G in our biological system, it's a function of the standard state free energy plus R T L my equilibrium. Here I don't have an equilibrium, right? I do have an equilibrium. It's not written as an equilibrium constant. We already know that our equilibrium is our products over our reactants, right? Our products, that would be G. Phosphoryl phosphate concentration. If I plug numbers in, delta G naught would just calculate 7,550 plus 8.35 temperature. That's the natural log. 3 times 10 to the 6 over 2 times 10 to the 4. My answer is negative 2,856 joules per mole. And how? How? What changed? Obviously, what changed? We deviated from our standard state conditions, right? Deviated from our standard state conditions. But what changed? Concentration of what? Everything, probably, right? Concentration change. That's the main idea. There's a change in concentration. So delta G is sensitive to changes in concentration, right? Changes in concentration. Hopefully this makes a lot of sense. We're going to talk about two ways. We just talked about one, right? Our first example would be our first example would be number one, which is concentration. Concentration changes. What question? How are we over? So I guess our question. How do we overcome a positive G naught? How do we overcome a positive delta G naught? Our first example are changes in concentration. And not just changes in concentration. Specifically in biological systems, in metabolic and in catabolic pathways, we are going to see not only concentration changes, but specifically removal product. Right? Because in standard state conditions, we have a bunch of stuff, and we're going to measure the equilibrium, and we have a bunch of reactant, we have a bunch of product. That's not what's happening in a cell, right? Especially, it's not what's happening in a system in which it lies in the middle of a long pathway. You have to take into account multiple things, right? Two things that you would have to take into account is production of your reactants, right? Because what's up?
Sorry.
You'd have to take into account production of your reactants and consumption of your products, right? If it is in the middle of a pathway, you have to take into account production of your reactants and consumption of your products. So concentration changes are one of the ways we can overcome, one of the ways these systems overcome positive delta G values, specifically removal of product, right? Because the smaller and smaller your numerator gets, if this equilibrium is true, if we're flooded with reactants and we're flooded with products, if we start taking away products, it's going to drive the reaction towards products, right? It's going to drive the reaction towards products. So hopefully that makes sense. Removal of products. Some unfavorable biochemical reactions are coupled with favorable biochemical reactions. Coupled with favorable processes. What do we mean coupled with favorable processes? This is where things like hydrolysis of ATP. So if we look at this first step of glycolysis, glucose plus inorganic phosphate is converted to glucose 6-phosphate. In the delta G naught, standard state change in free energy is positive 13.8. And this is big. It's big enough that this can't be overcome by thermodynamic changes in equilibrium. Removal of product. It's too big. Too big. So this reaction is coupled with the hydrolysis of ATP. Hydrolysis of ATP. ATP hydrolysis has a delta G naught of negative 30.5 kilojoules. And luckily, changes in standard state free energy among coupled reactions are additive. They are additive. So we're not physically adding these reactions together, right? Physically adding these reactions together. It's easy to think about in terms of glucose. We're looking at what's happening in this coupled reaction. We're generating an organic phosphate, we're using an organic phosphate, we're generating water, we're using water. Glucose and ATP. Making glucose 6-phosphate. ATP. Standard state change in free energy, negative 16.7. So 2 ways biological systems overcome positive delta G dot. Yes. Two ways these systems overcome positive delta G dot values. Changing concentration, specifically removal of product, right? Take that numerator away, it's going to throw the equilibrium towards products, right? Towards products. No matter how unfavorable it is, if you take away products, equilibrium is going to drive towards products. In situations where this isn't sufficient, you also see coupled reactions, unfavorable reactions, coupled with favorable reactions. When we talk about favorable reactions, your textbook will talk about a few different favorable reactions. And depending on what textbook you're looking at, I'll talk about the heat transfer. The one we're going to spend time talking about in class, and specifically in the pathways we're going to look at, is phosphoryl transfer, transferring phosphoryl groups. When we say phosphoryl transfer, we mean the transfer of a phosphoryl group, which is a PO3 group, not phosphate transfer, which would be a PO4 group. This is an example of phosphoryl transfer. Right? Transfer of the PO3 group to glucose. And when we break down these reactions, so glycolysis, first step of glycolysis right here. We'll dig into it when we get there next week. Speaking of phosphoryl transfer, we're going to go through and this is probably the last thing we're going to do today. The last thing will be hydrolysis of ATP. You will not find a reaction mechanism. Most likely, you won't find a reaction mechanism for this in the textbook. We're going to go through one. The reason we're going to go through one is because you need to know this. 2 is because it is a good. So I asked you at the very beginning of class, not the very beginning. I asked you before we got to enzyme mechanisms to review the hydrolysis of amide bonds under acidic conditions. Why did I do that? Because it looks a lot like serine proteases, right? It does. It really does. That's how serine proteases work. Instead of using a specific acid, they use a general acid, right? Or a general base. ATP, hydrolysis of ATP is a good foundation for understanding of phosphoryl transfer. A lot of these enzymes we're going to be talking about. Understanding the mechanism of hydrolysis of ATP gives you a really good hint of how these mechanisms or how these enzymes are going to prime their general surroundings for phosphoryl transfer for whatever reaction they're catalyzing. So hydrolysis of ATP. You have ATP, we just said this a second ago, right? ATP, H2O, going to ATP, inorganic phosphate, hydrogen. What is this? Hydrolysis of ATP. Water. Not APP. That's ADP. Y'all remember that song? Oh, you're down with OPP? Yeah, you know me. Remember that?
Yeah.
No.
You do?
Yeah.
Do you know how dumb I felt when I was a little kid? Because I was probably the only one that didn't know what OPP was, and nobody would tell me.
What is OPP?
OPP, other people's property. You never heard this song?
You heard that song before.
Oh, man, I'm just
You're making me relive my childhood nightmares all over again. Only kid on the block that didn't know what OPP was. ADP, sorry. ADP. Does this make sense, the way I drew this? So this is not ADP, this is ATP, right? That does make sense. That's ATP. I have an ADP plus a phosphate, which is ATP. Okay. The way I drew it like this because we're considered we're going to hydrolyze this phosphate. What's happening? What's the charge on this phosphate? Partially positive. Why? It's surrounded by a bunch of electronegative oxygens, right? So we do have a partially positive charge. We don't have a formal charge though, right? No formal charge. We do have a partially positive charge. So we have an electron deficient, we have an electron rich oxygen, and electron deficient phosphorus atom. Leaves us with an intermediate, and here we go. Before we do anything else, I'm going to say something real quick. What if this hydrogen was an R group? You're going to see this. This is, so imagine this is an R group and not a hydrogen, so we have this is how we're going to get phosphoryl transfer. So hopefully that helps when we start getting into mechanisms. We're going to look at enzyme mechanisms specifically, even if to make it go the first step of glycolysis. Think about if you can draw a reaction mechanism. First step, what we just drew right here, right? Phosphoryl transfer of a phosphate, an inorganic phosphate from ADP to glucose. And with this, you should be able to have an idea of what it's going to be. We're left with an intermediate positive charged oxygen. What can you tell me about the difference between this phosphorus and this phosphorus? What's the geometry around the two? What's the geometry on our first phosphorus? Tetrahedral. Tetrahedral, right? And this is we'll call this our gamma phosphate, right? Because it matters. So specifically, this reaction happens via the gamma phosphate. So gamma phosphate. This is our gamma phosphate, right? Third phosphate, ATP. Or NTP. So we have tetrahedral. What's our geometry here? Trigonal bipyramidal, right? Don't say trigonal planar. Trigonal planar. No, trigonal bipyramidal, right? And so we change geometry. We have a change in geometry. One of the things you're going to read about in your textbook asks you. It talks about roles of cations, and it really spends a lot of time talking about divalent cations. And I'll show you a nice graph of what effect does the concentration of cations have on the hydrolysis of ATP, and you're going to see it has a negative effect. Increased concentration of these divalent cations decreases the rate of hydrolysis of ATP. Why? I'm giving you a good example of why, a good hint of why, if you could think of what's happening from one step to the next step. Hopefully that answers your question. I'm not going to tell you why. I want you to answer why. Maybe a good exam question, maybe be a quiz question. We'll see. But that's something you should definitely read about, the effects of why does increasing concentration of magnesium, increasing concentration of divalent cations reduce the rate of hydrolysis of ATP. And this step from here to here should give you a pretty good idea of why it does that. You lose a hydrogen, you cleave an ATP, we are left with 3 ADP, inorganic phosphate, hydrogen. We'll talk about why a hydrogen, why not 2 hydrogens later. Yes, later. I probably wrote this wrong. That should have been in there. Maybe a little bit. Why? Because it's close to physiological pH, right? Do you know what the pKa of this phosphate is? This last phosphate.
6.5.
That's on ADP. ADP it's around 6.5. ATP it's around 7.7. So the pKa of these oxygens on phosphate actually, so we have 2 pKa's here. One of them is about 4, 3. One of them is pretty low. The next one is about 7. 7.5, 7.7. And we'll talk about that more about that on Monday when we get into our reasons for the large negative value of ATP hydrolysis. And we already said this value was about G naught of this. It's about, yes, I'm sorry. It's about 30.5. This isn't the only type of hydrolysis we can have. ATP can be hydrolyzed at the beta position. It's hydrolyzed at the beta position. It's going to produce a MP plus pyrophosphate. ADP plus water dehydrolyzed plus phosphate. And lastly, AMP can be hydrolyzed adenosine. And hopefully, we're going to stop here. Hopefully, by Monday, you'll be able to understand which one is the largest value. Oh, that one's actually kind of weird. That one may not make a lot of sense yet. Which one is the largest value? Which one is the smallest value? Why are some of them high energy, some of them low energy? Which one's the highest energy? I'll tell you right now. You would think this is weird because we always talk about hydrolysis of ATP, and we're going to talk about hydrolysis of ATP. But what if I told you the delta G naught of ADP is higher than ATP? That's weird, isn't it? It is weird. It is weird. Ask that question this week and see if you can figure out why. Why do you think it is? I'll tell you, it has something to do with metals, divalent metal cations. But that would be a good question. Another good exam question. Why is this under standard state conditions hydrolysis of ATP larger, slightly larger than ADP? And magnesium, that'd be a great answer. Okay, we'll finish this chapter on Monday. Y'all have a good weekend. Be safe.